This is the 11th video in a series devoted to complex analysis, and here we're going to look at a couple of really important results, including Gauss's mean value property and the strict maximum property. Okay, so before we do that, we need to recall a couple of things. One is from multivariable calculus, and then the other one is from some stuff we did in previous videos. So the first is Green's theorem. So it says the line integral over the boundary of a region, which we'll call del D, of p dx plus q dy, where p and q both have continuous first partials, is equal to the double integral over that region of the partial of q with respect to x minus the partial of p with respect to y. Okay, so I won't do any examples of this. I trust that you guys have seen that in a multivariable calculus class. And then next, let's recall the definition of a harmonic function. So we say a function h, which goes from d to c, where d is a subset of the complex numbers. That subset needs to have some sort of conditions like being simply connected as well. So this is harmonic if the second partial with respect to x of h plus the second partial with respect to y of h is equal to 0. Okay, so now that we've recalled all of that, let's look at our first property, or our first theorem that we will prove, and it is Gauss's mean value property. It says that if we have a harmonic function u from d to c, then for all z naught in D and r bigger than 0, satisfying the following condition, that the set of points z that are within r of z naught is totally contained in D, then we have the following equality. The value of u at z naught is equal to 1 over 2 pi, and then the integral from 0 to 2 pi of u of z naught plus r e to the I theta. So let's get a picture of what's going on here. So u of z naught, that's just the function evaluated at this point z naught here. And then this set could be described as this closed disk centered at z naught. So it includes all of those points in there. And then this integral over here, maybe without the 1 over 2 pi, just the integral, that represents the line integral around this circle right here that's centered at z naught with radius r. We can see that because this is exactly the polar parameterization of such a circle. So this z naught will be the center, r will be the radius, and e to the I theta gives you a unit circle. So this is going to be a unit circle extended by r and then shifted over to z naught. That gives us this circle like we just said. But then including this 1 over 2 pi is essentially finding the mean value of our function u on this circle. And what we have is that the mean value of this function u on this circle is exactly equal to its functional value at its center. Okay, so now that we've got a good idea of what's going on here, let's look at the proof. So starting with the proof, we'll look at r and then the derivative with respect to r of this guy right here. So that's going to be the integral from 0 to 2 pi of u z naught plus r e to the I theta d theta. Okay, nice. But now we can bring this d by dr inside of the integral, and we're allowed to do that based on the fact that u is harmonic. Okay, so let's do that. So that's going to give us r, and then we'll have the integral from 0 to 2 pi of the derivative of this guy right here with respect to r. But now as we bring that derivative inside, let's also transport this from the complex plane to the real plane. And that'll leave us with something like this. So d by dr, and then we have u evaluated at x naught plus r cos theta, and then y naught plus r sine theta. And then we have d theta here. So we're able to do that just based off of the fact that z naught plus r e to the I theta is equal to x naught plus r cos theta plus I times y naught plus r sine theta. That's of course if we take z naught to be x naught plus I y naught. But now we take the derivative of this with respect to r, keeping in mind that we have to use the chain rule here. So we have to go through the derivative of u with respect to x, and then the derivative of this with respect to r, and the derivative of u with respect to y, and the derivative of this with respect to r. So let's see what that gives us. So we'll have an r, and then an integral from 0 to 2 pi. We'll have the partial of u with respect to x. I'll leave off kind of my functional dependence just because it'll get a little bit too wordy here. And then the derivative of this with respect to r, but that's going to give us cos theta. And then the same kind of thing over here. So that'll be plus the derivative of u with respect to y, and then the derivative of that with respect to r, but that will be sine theta. And then all of this is d theta here. Okay, nice. But now let's bring this r inside so that we can rewrite this a bit. So this is going to be the integral from 0 to 2 pi of the partial of u with respect to x times r cos theta plus the partial of u with respect to y times r sine theta d theta. But we were called Green's theorem for a reason. And the reason we were called Green's theorem because this will simplify using Green's theorem. But in order to see that simplification, we need to keep the following thing in mind, and that is dx is equal to, let's see, minus r times sine theta d theta. And that's because the partial of x with respect to theta is that exactly, keeping in mind that x was equal to x naught plus r cosine theta. The derivative of cosine theta is minus sine theta. And then dy is equal to r times cosine theta d theta for the same sort of reason. So let's notice using that, we can rewrite our integral as the integral from 0 to 2 pi of minus the partial of u with respect to y dx plus the partial of u with respect to x dy. So again, that's just using these substitutions right here. Okay, but now we can apply Green's theorem. And when we apply Green's theorem, we get that this is equal to a double integral over that whole circle that we had on the last picture. But I'll leave off the bounds of integration for the double integral because as we'll see, everything will cancel. And then we have the partial of this with respect to x. So that's going to end up with the partial of u with respect to x squared, or the second partial. Because again, this is now playing the role of q over here. And then likewise, this is playing the role of p over here, but we've got a minus sign built in, so that turns into a plus. We have the second partial of u with respect to y, and then dA. But given the fact that u is harmonic, we know that this is equal to 0. But that's good. If that's equal to 0, then this whole thing is equal to 0. But if that whole thing is equal to 0, and we started with taking the derivative of this with respect to r, that means this must be a constant with respect to r. So again, the derivative of this with respect to r is equal to 0. That means that must be a constant with respect to r. Okay, so we'll bring that fact to the beginning of the next board, and then we'll finish the proof. So far, we showed that the derivative with respect to r of this integral was equal to 0, but that means it's a constant with respect to r. But if it's a constant with respect to r, that means its limit will be equal to itself. In other words, its limit as r approaches 0 will be equal to itself. So that means we can write this integral from 0 to 2 pi of u z naught plus r e to the I theta d theta will be the same thing as the limit as r goes to 0 from above of the integral from 0 to 2 pi of u z naught plus r e to the I theta d theta. Again, that's because this thing is a constant. But now what's happening with this limit like if we were not to view it as a constant? Well, this circle that we're integrating around would shrink to just its center, which is z naught. And so the value of this limit is really just the integral from 0 to 2 pi of u z naught d theta. But u z naught is a constant with respect to theta, which means the integral is quite simple. It just gives us 2 pi times u evaluated at z naught. But now looking at the extreme left and right hand side of what we built, we can see that just dividing by 2 pi will give us our desired result. Okay, nice. So now let's maybe get rid of this, and we're going to do a nice application of this theorem to calculating an integral. So we just got done proving Gauss's mean value property, and I've left off the hypotheses, but here we just have u z naught is the same thing as 1 over 2 pi, the integral from 0 to 2 pi u evaluated at z naught plus r e to the I theta. Now we're going to use this property to evaluate the following integral, the integral from 0 to pi of the natural log of sine theta d theta. And this is the start of a bunch of examples that we'll see throughout this course, where we're able to find interesting integrals of real valued functions using complex analytic methods. Okay, so let's see maybe how we can do this one. So we can rewrite this as the integral from 0 to pi of the natural log of, well, instead of writing sine theta, I'll write sine theta using its complex exponential form. And that will be 1 over 2i times e to the I theta minus e to the minus I theta. Okay, so we've got the natural log of that. And I'm going to do one more thing to start making this look a little bit more like what I've got over here. And that will be to factor in e to the I theta out. So that's going to give me the integral from 0 to pi of, let's see, minus natural log of 2i. I'll go ahead and take that out because we're dividing by 2i there. And then that'll be plus the natural log of e to the I theta times 1 minus e to the minus I times 2 theta d theta. So just to reiterate what happened here, I used logarithm rules to bring that natural log of 2i out. And then I factored this e to the I theta out. Now I'm going to use logarithm rules again to split this into pieces. So this is going to give me the integral from 0 to 2 pi of minus natural log of 2i. I'm going to keep that as an integral of its own, so d theta, and then I'll bring my minus sign out of the integral like that. And then I'll have plus the integral from 0 to 2 pi of the natural log of e to the I theta. But natural log of e to the I theta is just I theta d theta. And then finally plus the integral from 0 to pi. These should have all been 0 to pi. The integral from 0 to pi of the natural log of 1 minus e to the minus I 2 theta d theta. But now we can simplify each of these pretty quickly. Notice this is a constant with respect to our integration. So that gives me minus pi times the natural log of 2i. But that's just the natural log of 2 plus the argument of 2i, which is pi over 2. So here we're using the fact that the natural log of a complex number is the natural log of the modulus of that complex number plus the argument of that complex number, where here we're taking the principal branch of the logarithm, and that's the principal branch of the argument. And now I guess I should have an I here as well. So I need an I in there. And now we can integrate this pretty easily to see that we get I times theta squared over 2 evaluated at pi. So that's going to be pi squared over 2. But then we see that this guy right here will cancel with this guy right here, leaving us with just minus pi times the natural log of 2. Then I can fix this a little bit. So I'm going to add a limit as r goes to 0 from above to this, and then the integral from 0 to pi of the natural log of 1 minus r times e to the minus I 2 theta d theta. And that's just to keep that in the region where our logarithm function is harmonic, and that will be away from 0. Because notice that this guy right here is a circle of radius 1, but that's going to go in towards 0. And, natural log is not analytic there, so we're not good to go. Now we can start simplifying. So this gives us minus pi times the natural log of 2. And then we can use Gauss's mean value property on this integral to tell us that this is just the natural log of 1. You might say, well, this looks quite a bit different, or at least a little bit different than what we have over here. But the important thing about what we have over here is this interior is parametrizing a circle of radius r, which is centered at z naught. And this right here is parametrizing a circle centered at 1 of radius r. It's just parametrized a little bit differently. Notice that this 2 theta here makes up for the fact that we're only going from 0 to pi here. So we're actually okay. Okay, so like I said, this will be natural log of the center point of that center, but that's 1, natural log of 1 is 0, which means we have our final value, which is minus pi natural log of 2. Okay, so now let's move on to our next result. Now we're ready to look at something called the strict maximum principle. So let's see what it says. So we want to let h go from d to c be a bounded harmonic function where d is open and it's simply connected. So I haven't written that there because I don't really have room, but it's open and simply connected. Then if the modulus of f of z is less than or equal to m for all z in D, so that would be one of its above bounds, and the modulus of h evaluated at z naught is equal to m for some z naught in D, then h is indeed constant. So if it's bounded above and it reaches that maximum, then it must be a constant function. So I think that's pretty interesting. So now let's maybe jump into this proof. So let's consider the following set. So I'll call this set U, and it'll be defined as follows. So it's going to be all z in D, where the modulus of h of z is equal to m. So we know that that's not equal to the empty set. So this is a non-empty set because at least z naught is in here. So I said modulus, but I forgot to write it. The modulus of h of z is equal to m. So the modulus is equal to m, but this function is not equal to m. Well, maybe it's probably not equal to m because it's just on some circle of radius m around the origin. But we can multiply it by a complex number so that it is equal to m. So let's do that. So let's take lambda, which is a complex number where the modulus of lambda is 1, and when we take lambda times h of z naught, we get exactly m. So what is lambda? So I would say it's going to be the complex number with modulus 1 whose argument is negative the argument of h evaluated at z naught. That'll bring us back to the positive real axis. Okay, nice. And now we're going to consider a new function that's built out of this. So I'll call that new function u, and that function u will be the real part of lambda times our function h. Okay, so this is still a harmonic function. That's important to know, but it just only takes real values. Okay, so now what we'll do is take some z1, which is in our set U, and then we'll find some r. So it's going to be an r bigger than 0 such that the following set, so it's going to be all z such that z minus z1 less than r is contained totally in D. So since U is a subset of D, we're totally able to do this because D is an open set. And now we're going to look at the following object. And that'll be the integral from 0 to 2 pi of u evaluated at z1 minus u evaluated at z1 plus r e to the I theta d theta. Okay, great. And now by our previous result, we know that that is most definitely equal to 0 because that's exactly what we get over here if we just move some things around. Okay, so we've got that integral is equal to 0. But then since u is a real valued function and it's achieving its maximum at u of z naught, that tells us that this thing over here is always larger than this term over here, which means this is always bigger than or equal to 0. But if we're integrating a function that's always bigger than or equal to 0 and getting that it is equal to 0, that tells us that this entire thing is equal to 0. In other words, u evaluated at z naught plus r e to the I theta is equal to u evaluated at z1. I should have said z1. So that means the value of u at any point around a circle centered at z1 is equal to the point at the center. But that's going to be true for any r satisfying this rule right here. But what that tells us is that this set right here is not only within D, it's within U. So we have this is totally contained in U. But that's exactly the condition for U to be an open set. So that means that U is open. Okay, so now that we have U as open, we're almost done with the proof of this, but let's maybe get rid of this so we can finish it off nicely. Okay, so we just got done finished showing that U, which was defined as follows. So it was all of the points where the modulus of H reached its maximum was an open set. But now let's notice that there's a pretty interesting way that we can write U complement. So notice that U complement is going to be all Z in D such that the modulus of H evaluated at Z is strictly less than M. But using our function U that we used before, that's the same thing as all Z in D such that U evaluated at Z is less than M, because recall U is a real valued function. But now that's exactly equal to the pre-image of the set from minus infinity to M under the function U. But that's the pre-image of an open set. But then from real analysis, or really the topological version of continuity, we know that the inverse image of an open set is open. So that tells us that U complement is open. Okay, so now what do we have? We know that D is U union U complement, and that's a disjoint union. But it cannot be written as the disjoint union of two open sets and still be connected. But let's recall that it was connected. That was one of the things that we didn't write up here, but we said out loud. But since it's connected and it's written as the disjoint union of two open sets, one of these open sets must in fact be empty. Well, we know that U is not empty. That means that U complement must be empty. So we know this must be equal to the empty set, but that means the set U is really the entire set D. But then if we rewrite this as our real valued function U of Z being equal to M, that means our real valued function U of Z is always equal to M. But that means that lambda times our function H of Z breaks into a real part, which is exactly equal to M. Remember, the real part we set equal to U of Z, but we just argued that U of Z must be a constant, plus I times some imaginary part, which I'll just put as kind of a blob like that. But notice that imaginary part must be 0. If that imaginary part is ever non-zero, then H will achieve a modulus which is greater than M, but we know from our assumption up here that it never achieves a modulus greater than M. So in the end, we have lambda times H of Z is always equal to this value M, which means H of Z is a constant. So that finishes this proof. Okay, now we're going to look at a corollary of this and then some examples. Now we've got something called the maximum principle. So this is a corollary to what we just proved. So we want to start with a harmonic function H of Z on a bounded domain D. Let's recall that a domain was an open set that was connected. Also, we need this function to extend continuously to the boundary of D. Okay, so the D including the boundary of D will be a closed bounded set and thus compact, which is going to be important for the proof. Now, if the modulus of H of Z is less than or equal to M for all Z on the boundary, then the modulus of H of Z is less than or equal to M for all Z in the interior. So I've got a little picture of this right here. So here we've got a bounded set D, and here's its boundary right here. And this just says that the maximum must occur on the boundary. It can't occur on the interior. Let's recall that we just essentially proved that if the maximum occurs on the interior, then that function is a constant in the first place. Okay, so let's see how this proof goes. So we know H is continuous. So harmonic implies continuous, and then we've got extended continuously to del D. Furthermore, it's continuous on D union del D. So D including its boundary, which is compact. So let's write that, which is compact. But the fact that this is continuous and this is compact means it achieves its maximum for some point there. So let's write that as follows. There exists some Z in D union del D such that the modulus of H evaluated at this Z is equal to M. And now let's break this down into cases. So we'll have a first case and our second case. So our first case is that z is in D. But then by our previous result, that tells us that h of z is equal to m for all z in D. Remember, h of z must be a constant, and thus its modulus is always m. But m is most definitely less than or equal to m, so we've satisfied the result here. So our next case is that z is in the boundary of D, but in that case we're totally done already because we've achieved this setup. Okay, so let's maybe get rid of this and then we'll look at some examples. So we just got done proving something that's called the maximum modulus theorem. And what that essentially says, I've left out a lot of details, but this is how you want to remember it, is that functions achieve their maximum modulus on the boundary of a bounded set. So that's in stark contrast to what happens with real variables, where we are allowed to achieve maximums and minimums not only on the boundary, but at an interior point if it's a critical point, which is where the derivative is 0 or does not exist. Okay, so let's look at a couple of examples. So our first example will be f of z equals z squared plus 3z plus 1, and our D will be the unit circle. So that's going to be all z whose modulus is 1. Okay, so let's notice that f is analytic, so that's pretty clear. We actually proved like that all polynomials are analytic in a previous video, but that means that it's harmonic, but that means that the max is on the boundary of D, but that's going to be the unit circle. So that's going to be all z such that the modulus of z is equal to 1. But now let's notice that if the modulus of z is equal to 1, then that means that the modulus of f of z is less than or equal to the modulus of z squared plus 3 times the modulus of z plus 1. There we use the triangle inequality. But that's just equal to 1 plus 3 plus 1, which is equal to 5. So we've got the modulus of z is less than or equal to 5. And now the real goal is, can we find a place where it's equal to 5? And we can, and that's at 1. So let's note that f evaluated at 1 is equal to 5. So what we have here is that the modulus of f of z is less than or equal to 5 for all z in this open unit circle, where we've achieved this maximum at 1, which is on the boundary. Okay, so let's do one more example. So here we've got a slightly tweaked example. So we've got f of z is equal to z squared plus 3z minus 1. And now let's set D to be that closed unit disk. So by the maximum modulus principle, we know that the maximum modulus will occur on the boundary. So we might as well parameterize the boundary. And we can do that as follows. So z equals 1, so that's a unit circle. That's the same thing as the parameterization z equals e to the I theta, where theta goes between 0 and 2 pi. So that's a standard way to parameterize the unit circle. And now let's look at the modulus of f of z, which we're trying to maximize. But that's going to be equal to the modulus of z squared plus 3z minus 1. We'd really like to get that in terms of just this z, so we can do that by factoring a z out. That'll give us the modulus of z times the modulus of z minus 1 over z, and then plus 3, where I've rewritten things a little bit. But now I can plug this e to the I theta in here, and I have an e to the I theta for this, and I have e to the minus I theta for that. Then I've got e to the I theta minus e to the minus I theta. But if you recall, that's equal to 2i sine theta. So in fact, we have this is equal to the modulus of 3 plus 2 times I sine theta. Again, that's what these two green things with the minus sign combine to, this 2i sine theta. You might say, where did this modulus of z go? Well, recall that we're on the unit circle, so that is equal to 1. Okay, but we can find the modulus of this pretty easily because we have real part plus imaginary part. And the modulus of this will be the square root of 9 plus 4 times sine squared theta. But notice this maximum will occur exactly where the maximum of sine squared occurs, which is where sine either achieves the value of 1 or minus 1. So sine achieves the value of 1 at pi over 2. So that means theta equals pi over 2 will give us 1 kind of maximum value, and theta equals 3 pi over 2 will give us sine equals -1, which gives us sine squared equals 1. Regardless, what we'll see is that this is always less than or equal to the square root of 9 plus 4, which is 13. And I guess I should say that this exact maximum is achieved at these two values of theta. And you can plug those values of theta back into this parameterization to get those written in rectangular complex form if you want to. And doing that, we'll see that this is z equals plus minus I. So that gives us the maximum modulus. Okay, so let's get rid of this and then I'll leave you with some warm-up problems. So here I've got two warm-up problems for you. So the first is to evaluate the following integral, which looks pretty difficult, but if you recall Gauss's mean value property, it's not too bad. So it's the integral from 0 to 2 pi of sine squared of pi over 6 plus 2 e to the I theta. Then the second is an application of the maximum modulus theorem, and that's to find the maximum modulus of f of z for the modulus of z less than or equal to 1 of the following two functions. So the first is f of z equals z to the fourth plus z squared plus 1, and the second is f of z equals cosine of 3z. And that's a good place to stop.